Today, I'm going to show how Pytorch works with computer vision. This is a step-by-step guide, so check the link in description to download the source code available on my website. Download it and follow along. So let's start. This code starts by importing the Pytorch library, which is a popular open-source machine learning framework for building and training neural networks. It also imports the NN module from Pytorch, which provides all the necessary functions for building neural networks. Next, it imports Torch Vision, which is a library that contains datasets, models, and transformations for computer vision tasks. Then, it imports the datasets module from Torch Vision, which contains standard datasets for loading and processing images. ToTensor is another module imported from Torch Vision, which is used to convert images to tensors, a kind of multi-dimensional matrix that is used as the input for neural networks. Next, it imports Matplotlib, a library that is used for visualization and plotting. This will be used to visualize the images from the dataset. The print statement at the end checks the versions of Pytorch and Torch Vision to ensure they meet the minimum requirements for the code to run properly. In summary, this code sets up the necessary libraries and modules required for computer vision tasks using Pytorch. It also checks the versions to make sure they are up to date. The code is now ready to load and process images from datasets and build and train neural networks for computer vision tasks. This code sets up the training and testing data for a computer vision task using the FashionMNIST dataset in Pytorch. The first step is to import the necessary library, which in this case is Pytorch's datasets module. Then, the code specifies the location where the data will be downloaded to, which is the data folder. Next, the code sets up the training data by calling the FashionMNIST function from the datasets module. This function takes in several parameters. Train is set to true to indicate that this is for training data, and download is set to true so that the data will be downloaded if it is not already present on the computer. The transform parameter is set to convert the data from pile format used for images into torch tensors, which are required for processing by Pytorch. The target transform parameter is left as none, indicating that no transformations need to be applied to the labels. Finally, the code also sets up the testing data using the same FashionMNIST function, but with the train parameter set to false to indicate that this is for testing data. The rest of the parameters are the same as for the training data. Overall, this code sets up everything needed to download, process, and use the FashionMNIST dataset for training and testing a computer vision model using Pytorch. This code is used for computer vision tasks and specifically deals with image classification using Pytorch. The lines of code are used to retrieve the first training sample and its corresponding label from a dataset. The dataset is assumed to contain images and their corresponding labels, which are used for training a neural network. The first line of code uses the index 0 to specify that we want to access the first sample in the training dataset. This could be any number, depending on the size of the dataset and the number of training samples we want to work with. The next line of code assigns the first training sample and its corresponding label to two variables: image, and label. The purpose of this code is to retrieve specific samples from the dataset and use them for training a neural network. This process is typically repeated multiple times, with the goal of the neural network learning how to accurately classify an image based on its features. This code snippet is a fundamental step in the process of training a computer vision model and is commonly used in various applications such as image recognition, object detection, and facial recognition. This code is used to determine the shape, size, and dimensions of an image in computer vision using Pytorch. The shape here refers to the height, width, and number of channels of the image. To determine the shape, the code first accesses the image variable and then uses the .shape method to return the shape information. This method returns a tuple with the first element representing the height, the second element representing the width, and the third element representing the number of channels of the image. This code is useful for understanding the dimensions of an image, which is important for performing various computer vision tasks such as image classification, object detection, and image segmentation. Additionally, knowing the shape of an image is necessary for pre-processing and normalizing the data before feeding it into a neural network for training. The first line imports the necessary libraries to perform computer vision tasks using the Pytorch library. These libraries include Torch Vision, which provides datasets and models for computer vision, and Transforms, which allows for image transformations such as cropping, resizing, and normalizing. The next line sets the transformations to apply to the dataset. In this case, it resizes and normalizes the images. This is important for the models to perform effectively during training. The next four lines load the train and test dataset from Torch Vision, which includes datasets like MNIST, CIFAR10, and ImageNet. The train dataset is split into images and labels, while the test dataset is split into test images and test labels. This is done for both the train and test datasets. The final 4 lines print the length of each dataset, which is the number of samples in each dataset. This is important for keeping track of the size of the dataset and for ensuring that all images and labels are loaded correctly. Overall, this code sets up the necessary libraries, performs image transformations, and loads the datasets for a computer vision task using Pytorch. The first line of the code assigns a variable class names to the list of classes in the training data. This list contains all the different categories or labels of data that the model is expected to recognize and classify. The second line then assigns another variable class names to the same list of classes in the training data. Since this code is part of a computer vision with Pytorch, it can be assumed that this list of classes is used for training a model to recognize and categorize visual data. Both these lines are necessary to ensure that the model has access to the correct classes or categories of data during the training process. The first line of code imports a library called matplotlib.pyplot, which is used for creating and displaying plots. The second line assigns the first element from the trained data array to 2 variables, image and label. This element likely contains an image and its corresponding label. The third line uses string formatting to print the shape of the image variable. The fourth line uses the plt.imshow function to display the image variable on a plot. The squeeze function removes any redundant dimensions from the image. The fifth line sets the title of the plot to the label variable. Overall, this code is used to display an image and its label on a plot using the matplotlib library. This code creates a visualization of an image using Pytorch, specifically for computer vision tasks. The first line uses the matplotlib library to display the image, while the second line adds a title to the image based on the predicted class label. The squeeze function is used to remove any unnecessary dimensions and convert the image to grayscale for better visibility. This code is beneficial for understanding and analyzing image data and their associated predictions in a visually appealing manner. This code first sets a manual seed for randomness to ensure reproducibility. Then, it creates a figure object for the plot with a size of 9 by 9 inches. Next, it defines the number of rows and columns for the plot. In this case, there will be 4 rows and 4 columns. To plot each image, the code uses a for loop to iterate through the rows and columns and generate a random index from the dataset. This index is used to select an image and its corresponding label from the training data. The code then adds a subplot to the figure using the current iteration in the for loop. The image is plotted along with its label and the axis is turned off. This process repeats until all 16 images are plotted. Overall, this code plots a 4x4 grid of randomly selected images from the training data, along with their corresponding labels. This code imports the DataLoader class from the Pytorch library, which is used for loading and organizing datasets for machine learning tasks. The code then sets the hyperparameter batch size to a value of 32, which will be used to determine the number of samples in each batch. The train and test datasets are then turned into iterables by using the data loader, which splits the data into batches and shuffles it if necessary. The train data loader and test data loader objects are created for the train and test datasets, respectively. These objects can be used to iterate over the batches of data during the training and testing process. The code then prints out the data loaders and their lengths to confirm that they have been set up correctly. This step is important in order to ensure that the data is properly loaded and organized for the machine learning model to use. Given a training data loader, the first 2 lines of code extract the next batch of training features and labels from the data loader. The next function is used to retrieve the next batch, and the iter function is used to create an iterator that can be used to navigate through the data loader. The extracted data is then assigned to the variables train features batch and train labels batch. The last 2 lines of code are then used to print the respective shapes of the training features and labels batch. This is done to ensure that the batch size and dimensions of the data are as expected. The shape function is used to retrieve the dimensions of the batches, and it returns a tuple of numbers that represent the size of each dimension. This helps to check if the data is properly formatted and ready for training. This code is used to show a sample random image from a training batch. First, a random seed is set using the torch.manualSeed function to ensure that the random numbers generated are reproducible. Then, a random index is selected from the training features batch, which contains a set of images. This is done using the torch.randint function, which generates a random integer within a specified range. The size of the index is set to 1, indicating that only one index will be generated. This index is then converted to a scalar value using the .item function. Next, the image and its corresponding label are retrieved from the training batch using the random index. The image is plotted using the plt.imshow function with the specified color map. The title of the plot is set to the class name corresponding to the label. The plot axis function is used to remove the axis from the plot, making it cleaner. Finally, the size of the image and label are printed for reference. The first line of code initializes a layer called flatten model and assigns it the functionality of the flatten module. This module is used in computer vision tasks to flatten the input data into a single vector. Next, a single sample from a batch of training features, train features batch, is selected and assigned to a variable x. This sample has a shape of color channels height width, which is printed out in the next step. In the following line, the sample is put through the flatten model layer, performing a forward pass. This results in the sample being flattened into a single vector, which is assigned to the variable output. The next two lines print out the shape of the sample before and after flattening, showing the transformation from a three-dimensional array to a one-dimensional vector. Lastly, there are two lines of code that are commented out. Uncommenting these would print out the values of x and output, showing the actual data before and after the flattening process. This code defines a class called Fashion MNIST Model V0 that implements a neural network model using Pytorch for computer vision tasks. The class has three parameters: input shape, hidden units, and output shape, which determine the shape and size of the input, hidden, and output layers of the neural network. Inside the init method, the super function is used to inherit from the nn.module class, meaning the Fashion MNIST Model V0 class will have access to all the methods and attributes of the parent class. Next, the class defines a layer stack using the nn.sequential function, which allows us to stack multiple layers of a neural network. The first layer in the stack is the nn.flatten layer, which converts the input image into a vector, as neural networks prefer their inputs in vector form. The next two layers in the stack are nn.linear layers, which are fully connected layers that perform matrix multiplication between the input and weight matrices. The first nn linear layer has the input shape as the in features and hidden units as the out features, while the second one has hidden units as the in features and output shape as the out features. Finally, the forward method is defined, which takes in an input x and applies the layer stack containing the three layers to it, producing an output. This output is returned by the method. Overall, this code creates a neural network model with an input layer, a hidden layer, and an output layer, all connected by linear functions. The first line of code sets the random seed to 42, which ensures that the same set of random numbers are generated every time the code is run. The next line of code creates a model called Fashion MNIST Model V0 with an input shape of 784, which represents the number of pixels in the image 2828. It also specifies a hidden units parameter of 10, which determines the number of units in the hidden layer. Lastly, the output shape is set to the length of the class names, which represents the number of classes in the dataset. The next line of code uses the .to method to move the model to the CPU. This is important because the model will be trained on the CPU in the beginning. This code starts by importing the requests library, which allows for making HTTP requests within Python. It then imports the path library from pathlib, which helps with navigating and manipulating file paths. The code then checks if a file called helperfunctions.py exists, and if it does, it prints a message saying it already exists and skips the following steps. If the file does not exist, it prints a message saying it is downloading the file and proceeds to download the file from a specific GitHub URL using the requests.get function. Lastly, the file is saved locally as helperfunctions.py. This code is useful for ensuring that the necessary files are downloaded before running the rest of the code. This code imports an accuracy metric from a helper function called accuracyFn. The metric is used for evaluating the accuracy of the model's predictions. An alternative accuracy metric called torch metrics, accuracy can also be used for the same purpose. Next, a loss function is set up using the nn cross-entropy loss function. This function calculates the loss or error between the model's predictions and the actual labels of the data. This is an important step in training a model as it helps the model learn and improve its predictions. Finally, an optimizer is created using the torch.optim.sgd function. This optimizer uses a stochastic gradient descent algorithm to update the model's parameters based on the computed loss. The learning rate, which determines the size of the steps taken during optimization, is set to 0.1. This code prepares the necessary tools for training a computer vision model using Pytorch. This code imports the timeIt module, and specifically the default timer function as timer. This function is used to measure the time taken for a piece of code to run. The next line defines a function print_train_time that takes in three arguments: start and end time in seconds, and the device on which the computation is happening. Inside the function, the difference between start and end time is calculated and stored in the variable total time. Then, a statement is printed to the screen that displays the device and the total time in seconds. with the precision of 3 decimal places. Finally, the function returns the total time to the caller. This function can be used to measure and print the difference in time for training a computer vision model using Pytorch. The code first imports TQDM from the auto module, which is used for displaying a progress bar while the code is running. Then the seed is set to ensure reproducibility, and the timer is started to track the training time. The number of epochs is set to 3 for faster training. Next, a for loop is created to iterate over the 3 epochs using TQDM. Within this loop, the model is put in training mode and a training loss variable is initialized to 0. Another for loop is created to loop through the training batches. Within this loop, the following steps are performed. 1. A forward pass is made through the model with the current batch of data X. 2. The loss is calculated for the predictions Y pred and the true labels Y. 3. The loss is added to the training loss variable, accumulating it for the entire epoch. 4. The optimizer's gradient is set to 0. 5. The loss is backpropagated to update the model's parameters. 6. The optimizer's step function is called to update the parameters. After every 400 batches, the progress is printed to show how many samples have been seen. Once the end of the training loop is reached, the total training loss is divided by the number of batches, giving the average loss per batch for the entire epoch. Next, the code moves on to the testing phase. Variables are set to accumulate the loss and accuracy metrics. The model is put in evaluation mode, and the torch.inference mode context manager is used for any calculations on the test metrics. Then, a for loop is created to loop through the test batches. For each batch, the following steps are performed. 1. A forward pass is made through the model with the current batch of data X. 2. The loss is calculated for the predictions test pred and the true labels Y. 3. The loss is added to the test loss variable, accumulating it for the entire epoch. The accuracy is calculated by comparing the predictions to the true labels and added to the test accuracy variable. 5. Both the loss and accuracy calculations are performed within the torch.inference mode context manager. Once the end of the testing loop is reached, the total test loss and accuracy are divided by the number of batches, giving the average loss and accuracy per batch for the entire epoch. Finally, the train and test loss and accuracy are printed, and the total training time is calculated and printed using the timer function. This code is responsible for evaluating a given model on a test dataset, calculating the loss and accuracy of the predictions made by the model. The first line sets the random seed to ensure the same results are obtained each time the code is run. The eval model function takes in the model, data loader, loss function, and accuracy function as arguments and returns a dictionary containing the results of the model's predictions. Inside the eval model function, the model is set to evaluation mode, and the inference mode is enabled to speed up the prediction process. Then, with the help of a for loop, the model makes predictions on batches of data from the data loader. These predictions are then used to calculate the overall loss and accuracy for the model. Once the loop is completed, the loss and accuracy values are scaled to find the average per batch. The results are then returned in the form of a dictionary, including the name of the model's loss and accuracy. Finally, the eval model function is called to calculate the results for a specific model 0 on a test dataset. These results are stored in a variable called model 0 or results and can be used for further analysis. This code initializes the device variable to either CUDA or CPU, depending on whether or not a CUDA-enabled graphics processing unit is available. This allows for device-agnostic code, meaning that the code can be run on either a CPU or GPU without requiring manual adjustments. This is a code for creating a model in Pytorch for computer vision. In this code, a class called fashionMnistModel_v1 is created, which inherits the methods and attributes of the nn.module class. This class takes in 3 arguments: input shape, hidden units, and output shape, which specify the shape of the input, number of hidden units, and output size of the model. Inside the class, a layer stack is created using the nn.sequential method, which allows us to stack multiple layers together. The first layer in the stack is n.flatten, which flattens the input images into a single vector. This is followed by 2 linear layers, which perform a matrix multiplication between the input and weight matrices to generate a hidden representation. The first linear layer has input shape as its input size and hidden units as its output size. This is followed by a ReLU activation function, which introduces nonlinearity to the model. The second linear layer has hidden units as its input size and output shape as its output size. Again, a ReLU activation function is applied to introduce nonlinearity to the model. Finally, the forward method is defined, which takes in a tensor X as input and passes it through the layer stack created earlier. This method returns the output generated by the layer stack, which can then be used for further processing. Overall, this code creates a model with nonlinear and linear layers, allowing it to learn complex patterns and relationships in the input data. This code first sets the manual seed to 42, which ensures that the random numbers used by the Torch framework are consistent and predictable. Then it creates an instance of a fashion MNIST model, which is a custom model used for classifying fashion images. The model has an input shape of 784, which is the number of pixels in the input image, and 10 hidden units. The output shape is set to be the length of the class names, which is the number of classes that the model needs to classify. The toDevice statement sends the model to the GPU if it is available, which allows for faster computation. Finally, the last line prints the device where the model is currently located, which in this case would be the GPU if available. Overall, this code initializes a fashion NIST model and prepares it for training on a GPU. This code imports helper functions needed for computer vision in Pytorch. Next, it creates a loss function using the cross-entropy loss method. The optimizer is then defined using the SGD stochastic gradient descent method, which takes in the parameters of the model and the learning rate as arguments. This means that the optimizer will be used to optimize the model's parameters during training using the given learning rate. Essentially, this code sets up the necessary components for training a computer vision model in Pytorch. This code is used for training and testing a machine learning model, specifically in the field of computer vision using Pytorch. The code begins by declaring the model, data loader, loss function, optimizer, accuracy function, and device to be used. Then, it moves the model to the specified device, which is typically a GPU for faster processing. The model is then trained using a loop that goes over the batches in the data loader. Within this loop, the following steps are performed. 1. The input data and labels are sent to the GPU. 2. The model makes a prediction based on the input data. 3. The loss is calculated using the loss function and added to the training loss. 4. The accuracy is also calculated and added to the training accuracy. 5. The optimizer's gradient is reset to 0. 6. The loss is backpropagated to update the parameters of the model. 7. Lastly, the loop calculates the average training loss and accuracy for the entire epoch and prints them out. Similarly, the code also includes a test step that is designed to evaluate the performance of the model on a separate test dataset. The only difference is that the model is set to evaluation mode, and the gradients are not calculated or updated. This is because the purpose of this step is to only measure the performance of the model, not to update it. The average test loss and accuracy are then calculated and printed out. This code first sets a random seed in order to ensure reproducibility of the results. Then, the time begins to be measured using the time_at library. It sets the number of epochs to 3 and starts a loop over each epoch. Each time, the epoch number is printed and the trained test functions are called. Finally, the total time for the training of the model is calculated and printed. The first line of code sets the random seed for Torch, a deep learning library in Python. This ensures that the pseudo-random numbers generated throughout the code remain consistent, making it easier to reproduce results. However, this line will produce an error because the function eval_model uses a model that is not device agnostic. The next line calls the eval_model function and passes in arguments for the model, data loader, loss function, and accuracy function. This function is likely used to evaluate the performance of a trained model on a dataset. The results of this evaluation are then saved in the variable model1 results. The final line simply prints the results of the evaluation, which could include performance metrics such as accuracy, precision, and recall. These results can be used to assess the effectiveness of the model in the task it was trained for. First, the values are moved to the target device using the torch.manualSeed42 function. The eval_model function takes in the model, data loader, loss function, accuracy function, and device as inputs. The model's performance is evaluated by calculating the loss and accuracy for each batch in the data loader. The model's predictions are compared to the ground truth labels using the accuracy function. The loss function is used to calculate the model's loss. The values are then scaled to account for the size of the dataset, and the results are returned in a dictionary format. This process is repeated for Model 1, and the results are stored in the Model 1 results variable. This code allows for the evaluation of different models on different datasets using Pytorch, making it a useful tool for computer vision tasks. This line of code is checking the baseline results for a model called Model 0 results in a computer vision code using Pytorch. This likely means that the model has been previously trained, and this line of code is used to evaluate its performance on a set of data. The baseline results refer to the performance of the model before any further adjustments or improvements are made. This allows for a comparison to be made between the initial results and any changes made to the model. This code creates a convolutional neural network CNN class called Fashion MNIST Model v2, which is used for image recognition tasks on the fashionableness dataset. The input parameters of this class include the input shape, the size of the input images, the number of hidden units, which determines the complexity of the model, and the output shape, which corresponds to the number of classes in the dataset. The class is initialized with the super function, which inherits properties and methods from the nn module class, the base class for all neural network modules in Pytorch. Then, two convolutional blocks, block 1 and block 2, are created using the nn.sequential function, which sequentially combines different modules into a single module. The first block, block 1, consists of two convolutional layers, each followed by a ReLU rectified linear unit activation function, which introduces nonlinearity into the model. The kernel size and stride of the convolutional layers are specified, along with an impeep optional padding parameter. Padding is used to keep the spatial dimensions of the input and output the same, and in this case, it is set to 1. Lastly, a max pooling layer is added to reduce the size of the feature maps. The second block, block 2, is similar to the first one, with the difference being the number of input channels, which is the number of output channels from the previous block. This allows the model to learn more complex features from the input images. The classifier layer is created using the nn.linear module, which is a fully connected layer that takes in flattened input data. The output of this layer corresponds to the number of classes in the dataset. In the forward method, the input data X is passed through each of the blocks and the classifier layer, and the output is returned. Lastly, a model 2 is created using this class, which is then transferred to the specified device, e.g. CPU or GPU. This code first sets a seed value of 42 for generating random numbers. Then, it creates a sample batch of random numbers with the same size as an image batch. The batch contains 32 images with 3 color channels RGB, and each image has a height and width of 64. Next, it selects the first image from the batch for testing purposes. The code then prints out the shape of the batch and the single image, as well as the pixel values of the single image. This code is used in computer vision with Pytorch to create and manipulate batches of images for training and testing deep learning models. First, the code sets the manual seed for Pytorch to 42. This ensures that the results will be reproducible if the code is run multiple times. Next, a convolutional layer is created using the nn.conv2d function from Pytorch. This layer will take in 3 input channels, possibly the red, green, and blue channels of an image, and output 10 channels. The kernel size is set to 3, which means that the convolutional layer will slide a 3x3 filter over the input image. The stride is set to 1, which means that the filter will move 1 pixel at a time. The padding is set to 0, which means that no padding will be added to the input image. Then, the code passes a test image through the convolutional layer. This means that the convolutional layer will apply its filters to the test image and output a new image with 10 channels. If the Pytorch version being used is earlier than 1.1.0, this step might cause an error due to shape issues. Overall, this code can be used to create a convolutional layer with specific parameters and apply it to an image. This is a fundamental concept in computer vision and is often used in deep learning models for tasks such as image classification and object detection. This code adds an extra dimension to the provided test image using the Pytorch function unsqueeze. The unsqueeze function adds a dimension of size 1 at the specified dimension, in this case, dimension 0. This effectively creates a batch of 1 test image, which is required as input for neural network models in Pytorch. The dot shape at the end shows the updated shape of the test image, which would now have an extra dimension of size 1. This extra dimension can be used to perform batch operations on single test images, making the code more efficient and compatible with Pytorch models. This code is using a convolutional layer to process a test image in Pytorch. First, the code adds an extra dimension to the test image using the unsqueeze function. This is necessary because convolutional layers in Pytorch expect a batch dimension along with the image dimensions. Next, the code passes the test image through the convolutional layer using the convlayer function. This function applies a filter to the image, convolving it and producing a new output image. The resulting output shape is then returned by the dot shape function, which gives the dimensions of the output image. Overall, this code uses a convolutional layer to process an image and returns the resulting output shape. This code begins by setting the seed for the random number generator to ensure reproducibility of results. Then, a new convlayer, convlayer 2, is created with different parameters such as the number of input channels 3, which represents the number of color channels in an image, the number of output channels 10, the kernel size represented as a tuple with a width and height of 5, the stride, which indicates how much the kernel moves across the input image, and the padding, which adds zeros around the input image to ensure that the kernel can be applied to the edges. Finally, the new conv layer 2 is applied to a test image using the forward method, which returns the shape of the output after the convolution operation has been performed. This code is commonly used in computer vision tasks using Pytorch, as it allows for customization of the convolution operation. This code prints out the internal parameters of the conv layer 2 in the form of a Pytorch state dictionary. This dictionary contains the information about the weights and biases of the convolutional layer. These parameters are learned through the training process and are used to transform the input data into meaningful features. By printing out these parameters, we can analyze and better understand how the convolutional layer is processing the input data and potentially make improvements to the model. This code is used to get the shapes of weight and bias tensors within a convolutional layer. The first line prints out the weight shape of the convolutional layer, which is a four-dimensional tensor with dimensions out channels equal 10, in channels equal 3, kernel size equal 5, kernel size of 5. This means that the convolutional layer has 10 filters with a kernel size of 5 by 5 and takes in an input with 3 channels. The second print statement prints out the bias shape, which is a one-dimensional tensor with dimension out channels equals 10. This indicates that the convolutional layer has 10 biases, one for each filter. Overall, these lines of code give us information about the size and structure of the convolutional layer, which is useful for understanding and debugging computer vision models. This code first prints out the original shape of a test image, which is a three-dimensional array representing an image. Then, it prints out the shape of the test image with an additional dimension added using the unsqueeze function, which adds a batch dimension to the image. Next, it creates a maxpool2D layer, which is a type of pooling layer commonly used in convolutional neural network CNNs for downsampling the input feature maps. The maxpool layer variable stores this layer. Then, the original test image is passed through a conv layer, which is not shown in this code snippet. The conv layer performs convolution operations on the input image. The output of this layer is then passed through the maxpool layer, resulting in a downsampled feature map. The shape of this downsampled feature map is printed, allowing us to see the effect of the pooling layer on the data. First, we set a random seed using torch.manualseed42, which ensures that any random values generated later will be consistent in different runs. Then we create a random tensor with a size of 1, 1, 2, 2 using the torch.randn function. This tensor has 4 dimensions and contains random values. We print this tensor and its shape to see its contents. Next, we create a maxpool layer using the nnmaxpool2d function. This layer is used to downsize and simplify images by selecting the maximum value within a certain kernel size. We can change the kernel size to see how it affects the output. We pass the random tensor through the maxpool layer using maxpool layer random tensor. This creates a new tensor with a shape of 1, 1, 1, 1 as the maxpool layer selects the maximum value from the random tensor. We print this new tensor and its shape to see the results. Overall, this code shows how we can use maxpool layers in computer vision to select important features from an image and downsize its dimensions. This code is setting up a loss function and an optimizer for a computer vision problem using the Pytorch library. The loss function that is being used is called cross-entropy loss, which is commonly used in classification tasks. It calculates the difference between the predicted probability distribution of the model and the actual labels, and then updates the model parameters to minimize this difference. The optimizer being used is called stochastic gradient descent (SGD), which is a popular optimization algorithm for training deep learning models. It takes in the model parameters, in this case represented by model 2, and updates them using a learning rate of 0.1. The learning rate determines the size of the steps taken by the optimizer to minimize the loss function. A larger learning rate can lead to faster convergence, but it can also cause the model to overshoot and not find the optimal solution. Overall, this code is important for setting up the training process for a computer vision model and ensuring that the model is constantly optimizing and improving based on the selected loss function and optimizer. First, the code sets a random seed using torch.manualseed42, which ensures that the results will be reproducible. Then the code imports the default timer function from the timeit module, which will be used to measure the time it takes to train the model. Next, the code initializes a variable train_time_start_model_score2 with the starting time using the timer function. The variable will be used to keep track of the start time of the training process. After that, the code begins training and testing the model for a specified number of epochs, which is currently set to 3. For each epoch, the code prints the epoch number and starts a new line. Inside the for loop, the code calls the train step function, passing in the necessary arguments such as the data loader, model, loss function, optimizer, and device. This function is responsible for training the model on the training data and updating its weights based on the calculated loss. Next, the code calls the test step function, which evaluates the model's performance on the test data and prints out the loss and accuracy results. Once the for loop finishes executing for all the epochs, the code calculates the total training time by subtracting the start time from the current time using the timer function and saves it in the variable train time end model 2. Finally, the code calls the print train time function, which takes the start and end time variables and prints the total training time in a human-readable format. In summary, the code measures the time it takes to train and test the model for a specified number of epochs and prints the results in a readable format for the user. This code first defines a variable called model2results to store the results of the eval model function. This function takes in 4 parameters, namely the model2, the test data loader, a loss function, and an accuracy function. The eval model function then evaluates the performance of the model2 on the test data using the provided loss function and accuracy function. Finally, the results of this evaluation are stored in the variable model2results and can be accessed for further analysis or comparison. The first line imports the pandas library under the name PD, which is used for data analysis. Then, a variable compareResults is created, which is assigned the value of a pandas data frame. This data frame contains 3 sets of model results, namely Model 0 results, Model 1 results, and Model 2 results. This means that each set of results is organized into columns and rows within the data frame. The data frame serves as a convenient way to compare the results of the different models in a structured and organized manner. It allows for easy visualization and analysis of the results, possibly leading to insights on which model performs better or worse. This code adds the training time for each model to a results comparison called compareResults. First, it creates a new column called training time and assigns it to a list of training times for each model, where the values were previously calculated and stored in variables called total train time model 0, total train time model 1, and total train time model 2. Finally, the updated compareResults is saved and potentially used for future comparisons between these models. This code visualizes the results of a computer vision model by creating a horizontal bar chart. The chart compares the accuracy of different models, with the x-axis representing the percentage of accuracy and the y-axis representing the name of each model. The compareResults variable is used to set the index of the chart to be the model names, and the model act column is used to plot the accuracy values for each model. The x-label and y-label functions are used to label the axes of the chart with appropriate titles. This code allows for a quick and easy comparison of model performances, helping to identify the most accurate model. This code takes in a pre-trained model and a list of data as inputs. First, it initializes an empty list called predprobs. Then it sets the model to evaluation mode using model.eval. This mode is used when we are making predictions as opposed to training the model. Next, the code enters a with block, which specifies inference mode. This is a context manager that temporarily changes the behavior of certain operations, in this case, the operations inside the for loop. This allows us to do efficient inference on the GPU. Inside the for loop, first the input sample is prepared by adding an extra dimension and sending it to the device specified, usually the GPU. Then, the input is passed through the model sample to get the raw logit. After that, the logit is converted into a prediction probability using the softmax function with the specified dimension. Then the prediction probability is added to the predprobs list. Since the prediction probability is on the GPU, it is converted to CPU using the .cpu function before it is appended to the list. Once the for loop is finished, the predprobs list is stacked to convert it into a tensor. This tensor is then returned as the final output containing the prediction probabilities for all the input data. The first 2 lines import a library for generating random numbers and sets a seed so that the numbers generated will be the same every time the code is run. The next 2 lines create 2 empty lists, one for storing test samples and one for storing corresponding labels. Then, in the for loop, the random.sample function is used to randomly select 9 samples from a larger list called test data. The samples and their corresponding labels are then added to the empty lists created earlier. Finally, the code prints out the shape and label of the first test sample, along with its corresponding class name. This will allow the user to verify that the data is being loaded correctly. This code is making predictions on test samples using a computer vision model called Model2. First, it calls the function makePredictions, passing in the model as well as the test samples. The output of this function is assigned to the variable predprobs, which will contain the prediction probabilities for each test sample. Then the code prints the first two prediction probabilities by accessing the first two items in the list of probabilities using the v2 index. This allows for a quick check of the model's performance on the initial test samples. This code is used for making predictions on test samples using a pre-trained computer vision model in Pytorch. The predictions are stored in a variable called predprobs. The makePredictions function takes two arguments, the model2 and the test samples. This function uses the model to make predictions on the test samples and returns a list containing the prediction probabilities. The last line of code simply prints out the first two items in the list, which represent the prediction probabilities for the first two test samples. This allows for a quick visual check of the predictions. This code is used in computer vision with Pytorch to convert prediction probabilities into prediction labels. The argmax function is used to find the index of the maximum value in each row of the prediction probabilities matrix. This index represents the predicted class label. By using the div_1 parameter, we are finding the maximum value in each row instead of the entire matrix. The result of this operation is an array containing the predicted class labels. Finally, the numpy function is used to convert this array into a numpy array, which can be processed further or used for evaluation. This code compares the predictions made by a model in a computer vision task stored in the variable pred classes and the actual labels for the test data stored in the variable test labels. It checks if the format of the predictions is the same as the format of the labels. This is important in order to evaluate the accuracy of the model and to ensure that the predicted classes can be compared with the true labels. This code is used to plot predictions made by a computer vision model using Pytorch. The plt.figure command creates a figure with 9 rows and 9 columns. The for loop iterates through each of the test samples and creates a subplot for each sample. The sample image is plotted using plt.imshow with a grayscale color map. The prediction label is then obtained from a list of class names, and the truth label is obtained from the test labels. The title of the plot is created with the predicted and true labels. Depending on whether the prediction is correct or not, the title color is changed to green or red, respectively. The plt.axisFalse command turns off the axis labels and ticks for a cleaner plot. Overall, this code is used to visualize the predictions made by the computer vision model and compare them to the true labels. This code is used for making predictions with a trained model in the field of computer vision using the Pytorch library. The first step is to import the TQDM library, which allows for creating a progress bar to track the progress of the code. Then the code creates an empty list called ypreds, which will be used to store the predictions made by the model. Next, the model is set to evaluation mode using model2.eval. Then, the code uses the torch.inference mode context manager to temporarily set the model to inference mode. In this mode, the model will not track the gradients, making the code more efficient for prediction purposes. Next, the code iterates through a test data loader using the TQDM library to generate a progress bar. Inside the loop, the data and targets are sent to the target device, which is usually a GPU if available, using X_device and Y_device. Then, the forward pass is performed on the model using X as the input, which generates logit outputs. The predictions are then converted from logits to prediction probabilities using the softmax function, and the argmax function is used to choose the label with the highest probability. The predictions are then appended to the ypreds list, and this process continues until all the data has been iterated through. Finally, all the predictions are concatenated into a tensor and put on the CPU for evaluation. This code first checks if the package torchmetrics exists, and if it doesn't, it will try importing it. It also tries to import the package mlxtend and prints the current version of mlxtend. If the version is less than 0.19.0, it will raise an error. If both packages are successfully imported, the code will continue to execute. However, if any of the packages cannot be imported, the code will use the command -pip install q torchmetrics-u mlxtend to install the latest version of both packages. This may prompt the user to restart the runtime, which may be necessary for the packages to be successfully imported. After that, the code will try to import both packages again and print the mlxtend version. This ensures that the required packages are available for the rest of the code to use. This code first imports the upgraded version of mlxtend, a library used for machine learning with extensions, and then prints the version of mlxtend that is being used. Next, it checks to make sure that the version being used is 0.190 or higher. This is important because some of the functions used in the code may require this specific version or higher in order to run correctly. If the version is below 0.19.0, the code will break and will not be able to execute properly. By checking and asserting the version, the code ensures that it will be able to run without any issues. This code utilizes two libraries, torch metrics, and MLXX to implement a confusion matrix in a computer vision task using Pytorch. First, the necessary libraries are imported. Then a confusion matrix instance is set up and initialized with a number of classes in the dataset. The instance is then used to compare predictions, ypred tensor, to the actual targets, testdata.targets, resulting in a confusion matrix tensor. Finally, the confusion matrix is plotted using matplotlib, using the class names and a desired figure size. Overall, the code helps to evaluate the accuracy of the predictions by visually representing the number of correct and incorrect predictions for each class in the dataset. This code first imports the path module from the Python standard library pathlib. This module is used for manipulating file system paths and can be used to create new directories or files. Next, the code creates a path object named model_path, which represents a subdirectory models. The next line calls the mkdir function on this path object, which creates the models directory if it doesn't already exist. The parents equals true argument ensures that any necessary parent directories are also created. The exist OK equals true argument prevents an error from being thrown if the models directory already exists. Next, the code sets the name of the model as model name. Then a path object named model_save_path is created by concatenating the model path and model name variables using the / operator. This represents the full path where the model file will be saved. Finally, the model state dictionary is saved using the torch.save function. This takes two arguments, obj, which is the model state dictionary, and f, which is the file path where the state dictionary will be saved. The state dict function is used to retrieve only the learned parameters of the model, rather than the entire model. A message is printed, indicating where the model was saved. This code creates a new instance of the fashion MNIST model v2 class, which is used for image classification using computer vision in Pytorch. The input shape parameter specifies the number of input channels in the model, while the hidden horn units parameter controls the size of the hidden layer. The output shape parameter determines the number of output classes the model can predict. Next, the code loads the saved state dict of the model, which contains the learned parameters and weights. This step is necessary for using a pre-trained model for inference. Finally, the code sends the model to the GPU for faster computation. This code is used to evaluate a loaded model that has been trained for computer vision tasks using Pytorch. First, we set the seed for random number generation in order to ensure reproducibility. Then, we call the function evalsModel to evaluate the loaded model. This function takes in 4 arguments: the model we want to evaluate, a data loader for the test data, a loss function, and an accuracy function. The test data is divided into batches using the data loader, and the model's predictions are compared to the expected outputs using the specified loss and accuracy functions. Finally, the results of this evaluation are stored in the variable loaded model2 results. This allows us to assess the performance of our loaded model and make any necessary adjustments before using it for real-world applications. Equals model2 inputs. This line of code executes the model2 function with the inputs variable as the input. The model2 function, which likely defined earlier in the code, contains a series of steps and operations that are designed to process and analyze the inputs. These steps and operations could include things like data preprocessing, feature extraction, and model training, depending on the specific application of the code. Once the function has been executed, the model2 results variable will store the output or results of the model2 function, which can then be used for further analysis or processing. Overall, this line of code is an essential component of the computer vision process, as it applies a trained model to the given inputs to generate results and insights. In computer vision with Pytorch, the code checks to see if 2 sets of results from different models are close to each other. This is done by using the torch.isClose function, which compares the 2 sets of results and returns a Boolean value indicating whether they are within a certain range of each other. The ATOL absolute tolerance and RTOL relative tolerance parameters control the range in which the results can differ and still be considered close. If the results are not close, there is a possibility that there is an error in one of the models. This type of comparison is important in computer vision tasks, as it can help identify potential problems or discrepancies between different models.